Good morning friends, welcome back. In our previous lecture we are talking about how to find the velocity of UAV, right? So we derived that if you know the differential pressure, that is if you can measure the total pressure, static pressure, and if you know the density, you will be able to find the velocity. So we measure this total pressure, right, with the help of pitot tube, and static pressure with the help of static tube, static pitot tubes and corresponding sensor, pressure sensor, static tube, right, connected to a pressure sensor, static pressure measured with the help of static tube connected to sensor, pressure sensor. And to know the density at that particular altitude, right, we derived standard atmosphere, equations for standard atmosphere. So where we observed there are some altitudes at which like the temperature changes with altitude and the pressure and density also changes with. And standard atmosphere is a plot that represents the variation of this temperature with altitude, right? So let us limit ourselves right now to the first two layers. This is a gradient layer. And the slope A is equal to minus 6.5 Kelvin per kilometer, right? So this gradient layer extends up to 11 kilometers altitude. And this is the sea level, this is the temperature variation. And the sea level temperature is 288.16 Kelvin, right? And up from 11 to 25 kilometers, it is observed that the temperature almost remains constant, and the corresponding layer is termed as isothermal layer. Right? So at 11 kilometers, we observe it is 216.66 Kelvin. Right? Yes. So to find out the temperature, pressure and density at different altitudes, we have derived for gradient layer we can use these equations or relationships. AR minus 1. So these two relationships stands for gradient layer, where if you know the altitude, you can find the corresponding temperature at that particular altitude by the definition of this lapse rate, which is dt by dh. This equals to T2 minus T1 is equals to A into H2 minus H1. T2 is equals to T1 plus A into H2 minus H1. Right? If you know the altitude of your flight, you will be able to find out the corresponding temperature here. Right? So using this temperature and the sea level temperature, and you know the sea level density, you will be able to find out the density at the required altitude as well as the pressure at the required altitude. So what are these STP conditions? Standard temperature, pressure, P at sea level, right, at STP or sea level, you have P is 1 atmosphere, which is 1.01325 into 10 to the power of 5 Pascal. At STP we have density is equals to 1.225 kg per meter cube and temperature is 288.16 Kelvin, and the R that we are using here is universal gas constant, which is 287 joule per kg Kelvin, right? And G naught is 9.81 meter per second square. Okay. Now, yesterday we solved few examples, right, in which we assume that the altitude is known, altitude is given, and the corresponding velocity is obtained, right, by means of the measured either pitot pressure or the static pressure. Now, but who is giving this information about your altitude? How do you know at what height your UAV is flying? So, in our previous examples, we considered altitude is given, right? But how do you know who is going to give that? Oh, let us take some examples so to address this, right? Example 3, if I am not wrong. Right? Consider the differential pressure measured by the pressure sensor. So, in some cases we can also have differential pressure sensors, right? Instead of measuring separate pressure separately from pitot tube and static tube, what you can do is you can connect to a differential pressure sensor, right? One can be P naught, the other can be PS. So you can have a pitot tube you can connect pitot tube for to this total pressure port, and then you can have a static tube at the same time. So you will get PS from here, P naught from here. Right? So you can use a differential pressure sensor directly. So this differential pressure is measured by this differential pressure sensor, right? Instead the difference is of a UAV cruising at 30 meters per second is 409.05 Pascal, right? Find the corresponding altitude of flight. question is clear here. We have P naught minus Ps is equals to 409.05. You have velocity, cruise velocity is 30 meters per second. Now you need to find what is the altitude at which you are flying. So let us constrain ourselves, like all the examples that we are going to solve is for the gradient layer till 11 kilometers, right? So even commercial aircrafts fly till 11 kilometers. Now we have V infinity is equals to square root of 2 times P naught minus Ps by rho, right? And say if I want to find out H, right, either I need to know what is the density at that altitude or the pressure at that altitude, static pressure at that altitude, right? So let us see what we can find from this given data. Rho is equals to P naught minus Ps divided by half V infinity square, right? From here I can get what is the density, because the P naught minus Ps is 409.05 twice divided by 900. .909, yes, almost like 0.909 kg per meter cube. Now I know density at a height h, right? Or say let it be the density at our altitude, right? It's at the corresponding altitude of flight. Now using this relationship, what we have is T2 by T1 is equals to rho 2 by rho 1 1 by minus G naught by AR minus 1, right? T2 is equals to T1 times what is rho 2 is 0.909 and 1.225 kg per meter cube. So rho 1 is here sea level density and T1 is the sea level temperature. Minus 9.81 divided by minus 0.0065 into 287 minus 1. So what we have, T2 is equals to 288.16 . What we get from here is 268.624 Kelvin, right? You know T2 by using the definition of lapse rate. You can find what is the H. Since you have dt, you can find dH, right? So using the definition, A is equals to dt by dH, right? dH is equals to dt by A, that is equals to 288.16 minus 268.624 divided by minus 0.0065. This is minus of minus, T2 minus T1. This is T1 and T2, right? This equals to, which is approximately 3 kilometers. this is H2 minus H1, which is H, right? Because H1 is 0 here, sea level condition. Now you got geopotential altitude as 3 kilometers, right? Now you have to convert this 3 kilometers to geometric altitude. We have H is equals to R into Hg by R plus Hg. Right. This implies Hg is equals to R into H divided by R minus H. Right. So R here is approximately 6400 kilometers. Radius of Earth. R is the radius of Earth here. So Hg turns out to be 2.99 2.9985 kilometers. So the difference is hardly 1.5 meters. Right? Difference between geometric altitude and geopotential altitude. Assuming that there is no onboard GPS with which you can't, I mean, that's one source where you can get the altitude of flight, right? Assuming that there is no onboard GPS, now with the absolute pressure, whatever you are going to measure, right, how to find out the corresponding altitude. So this problem will address that situation, right? So let's take another example. Example 4. The static pressure sensor measures the pressure sensor of a UAV measures pressure of 53.75 kilopascals. Find the altitude of flight of this UAV. So what you have here is PS, a static pressure, or P at a particular altitude H, right, is equals to 53.75 kilopascals. Okay. Now we need to find out the corresponding altitude of flight. So we can use this relationship PH by P sea level, right? P1, let us say, is equals to T at that altitude by T at sea level raised to the power of minus G naught by AR, right? This is T at that altitude by 288.16 is equals to 53.75 kilopascals divided by 1.01325 kilopascals raised to the power of minus 9.81 divided by minus 0.0065 into 287. Right. Now the temperature at this altitude is equals to 255.66 Kelvin. Right. So we know from the definition of lapse rate again, A is equals to dH by dt by dH. Right. We have T2 is equals to T2 minus T1 is equals to by A is equals to dH, right? That is H2 minus H is equals to H. Equals to .255.66 minus 288.16 divided by minus 6.5 into 10 power minus 3. H is equals to 5 kilo. Right? So, and the corresponding Hg is 4.996 kilometers. Right? Right, and the corresponding geometric altitude is approximately 4.996 kilometers. So, what we have done here, in the question it is mentioned we have a static pressure data from the sensor, which is about 53.75 kilopascals. By using this static pressure, we found the corresponding temperature at that altitude, right, by using gradient layer equation. And with the with the help of definition of this lapse rate, we are able to find out the corresponding altitude of flight. And this geopotential altitude turned out to be 5 kilometers. And with the help of the relationship between geopotential altitude and the geometric altitude, we figured out geometric altitude to be 4.996 kilometers. Now, let us look at an aircraft. Let us say this is my UAV, which I am interested in. Okay. Yeah, fine. So, why do this aircraft fly? One simple answer can be, there is some force which is opposing this, right? Right? Let us term this force as lift. Right? And how lift is generated? Since we are talking about a fixed wing UAV, we need to move this aircraft at a required velocity. Who is moving this aircraft? Thrust is the force that is helping the aircraft to move at the required velocity, right? And there is some penalty at the same time for generating lift, as well as since we are moving in a fluid, right, there can be friction. So, because of which there is a opposing force called drag. These are the 4 forces that we need to study here, right? First to understand before start designing it. Now, who is generating lift? Now, let us look at the anatomy of the aircraft, right? So let us assume this as an aircraft, right? So you have some of the major components are wing, horizontal stabilizer or tail, vertical stabilizer. Or vertical tail, right? And we have a propulsion system, engine. Here it will be on either side, right? You can have a single engine as well in some of the aircrafts. So you have fuselage, and then undercarriage, right? Now major components which are fixed. Let us say for a conventional aircraft, what are the fixed components and what are the moving components, right? So fixed is like you have wing, you have horizontal tail, you have a vertical tail, fuselage, right? So we also have some moving components, right? So why do we need them? To control the orientation of this aircraft. So hence these moving components are also known as control surfaces. Some of these moving components are known as control surfaces, right? So we have something on elevator as well as, so we have something on horizontal tail called elevator. It's a moving surface, right? Which helps to control the nose up and nose down motion, right? And there is a moving component on this vertical tail called rudder, which helps you to turn left and right, right? And there are control surfaces on wing as well, ailerons, which helps you to roll, right? So we need to mention various motions that are possible with an aircraft, right? It's worth mentioning here, right? So aircraft is considering it as a rigid body, right? And rigid body in space have 6 degrees of motion, right? What it can do, it can move, it can translate. So it total have 6 degrees of freedom. Freedom, 3 translational, 3 rotational, right? So this rotational or the orientation of this aircraft are controlled by this control surfaces, right? Can be controlled by this control surface. So assuming this as the CG of the system and be the coordinate origin of this coordinate frame, whatever I am considering now. Right. Let us consider a right-handed coordinate system, right, where x cross y is z here. So the translational along x, along y, along z are the, it can other 3 degrees of freedom, right, linear translation, and then there is a angular rotation possible here. So let us start with x-axis. The rotation about x-axis is known as roll, right? What is the positive roll now? We have to define the convention also, right? So it follows the right hand thumb rule. Stretch your thumb along the positive x axis. The curl of your fingers will give you the positive rotation about the respective axis. Now, the positive roll will be, this is the right wing, say starboard, and the left wing or port side, right? So right wing going down is a positive roll, right? So you have roll, right? Similarly, and this roll is controlled by this ailerons, right? You can control the rolling motion by deflecting the corresponding control surfaces called ailerons here, right? And what about rotation about y-axis? Known as pitch, right? Pitch. So the positive pitch will be nose up. If the nose is going up, it is a positive rotation about y-axis. If the nose is going down, it's a negative rotation about y-axis. Similarly, you have yaw, right? If the right wing coming back, it is a positive yaw. Yeah. So pitch, rotation about y-axis can be controlled by elevator. We'll see how we can do that at a later stage, right? At the same time, yaw can be obtained by means of rudder deflection, right? Okay. So the moving surfaces we have with wing is aileron for control, and you have flaps or high lift devices, flap, which are used to enhance the lift, right? We saw that lift is essential. We nomenclatured just now a force that opposes the weight, right? So lift. So we need to have, enhance, if you want to enhance the lift at a lower velocities, we need to operate this flaps, right? And you have flaps. At the same time, you also have spoilers, which can sometimes be used as a control surface as well. You also have spoilers. So the basic aim of this spoiler is to reduce the lift, disturb the flow, yeah, and increase the drag. Okay. And how about horizontal tail? What you have is a elevator. It can be a split elevator as well, right? You can have 4 such split elevators to have the differential control right there. And you have vertical tail chord, and the corresponding control surface is known as rudder, right? So how to control the speed? So one variable that we have here, one control that we have is by varying the thrust, right? So thrust is often considered as a control input. Okay. Right? So we just now saw wing is one of the major component, right, of this aircraft. Right. Let us cut this wing. Let us say this is your some say center line or fuselage reference line, whatever, right? Let us say this is your wing, right? What happens if I cut this wing? you will often find a profile similar to this. Right? So this profile is known as airfoil, which is a 2D wing or infinite wing. Wing or infinite. Okay, so this aerofoil is responsible for generation of lift. How efficient how efficient the lift will be. Like, so you can, there are many ways to generate. You can also use a flat plate, right? So this shape speaks a lot about how efficiently you can generate the lift, right? So let us look at the nomenclature of this aerofoil first. So let us consider an arc or a line like this, right? Let us say this is, let us nomenclature it as mean camber line. So what is this mean camber line, right? Now, if I want to draw an aerofoil with the help of this mean camber line, what should I do? No? I can build the entire aerofoil with the help of this mean camber line, right? So let us say I know the thickness distribution at each and every point, right? Thickness is measured perpendicular to the mean camber line, right? At that particular point, right? Now say if I have a series of points, because if I vary the points along this camber line, I will get the thickness distribution. Let us say if I have that information, right, I will be able to plot upper and lower boundaries, right? These upper and lower boundaries are my upper surface and lower surface of aerofoil, right? And now obviously, since this thickness is a distance measured, right, from the upper surface to the lower surface perpendicular to the mean camber line, right? So here the thickness distribution is symmetric about this mean camber line, right? You understand? So this mean camber line will be the midpoints of the thickness at that particular location, right? So mean camber line can be defined as locus of midpoints of thickness of an aerofoil, right? So it's a locus of midpoints of thickness. Thickness, right? And you have upper surface and lower surface here, and you have thickness, which is the distance between upper surface and lower surface, which is measured perpendicular to this mean camber line. And the starting point of this mean camber line is a leading edge, so mean camber line or camber line, right, MCL. And the aft point of this mean camber line is trailing edge. This mean, right? A straight line joining this leading edge and the trailing edge is known as chord line. This is my chord. Straight line joining leading edge and trailing edge, right? Now comes the camber. The distance between this mean camber line and chord line is known as camber. Mean camber line and chord line, right? Okay, got it? Now say if the camber is 0, what happens? What is camber 0? When the mean camber line coincides with this chord line. So in that case, the thickness distribution will be symmetric about chord line. So when there is camber, the thickness distribution is always symmetric about mean camber line, but it is not symmetric about this chord line, right? When there is a camber. But when camber is 0, the thickness distribution is symmetric. So it's like the upper surface is a mirror image of bottom surface about the chord line, right? So in that case, this is how an aerofoil look like. This is your chord line and this is your mean camber line. Both coincides with each other, right? So, and you have equal thickness distribution. These two are equal, right? This is your leading edge, this is your trailing edge, right? This particular aerofoil is known as symmetric. Symmetric aerofoil. So this aerofoil is known as cambered aerofoil because it has a camber. Cambered airfoil, right? So if this camber is above the chord line, then it is known as positively cambered aerofoil, right? If this camber is below the chord line, then it is known as negatively cambered aerofoil. So you have two such aerofoils known as positively cambered and negative camber. Negative camber, positive camber and negative cambered aerofoils, right? If I make a wing out of this symmetric aerofoil, I have a symmetric wing, and if I make a wing out of this cambered aerofoil, I'll have a cambered wing, right? So let us see how to plot an aerofoil. Ultimately, what do you require? You require upper surface and lower surface. That's it, right? And something called leading edge radius, right? So this curvature, which is tangent to the upper and lower surface, right, is known as leading edge. The radius, if you draw a circle with a radius such that this circle becomes tangent to the upper and lower surface, right? So that radius is known as leading edge radius. We call this as leading edge radius. Okay. Now how can I plot this airfoil? When I say plot here, I need the coordinates of upper and lower surface. how can I plot it? Or say how an aerofoil software works. Say if you want to design a new aerofoil, what all you need to do, right? You have to start with. So the information that I require is, you can see the camber is varying with respect to the mean camber line, is varying as the chord varies, right? Let us say you have a chord here, at each and every location of this chord, there are corresponding coordinates for this mean camber line, right? Say if I have the coordinates of mean camber line, say this is, let us say C is my mean camber line, YC as a function of chord, or say X, right? Okay. Say this is my y-axis and this is my x-axis, right? Now let us assume the chord is along this x-axis. Okay. Fine. So let us consider my chord is along this x-axis, right? And if I know the equation of this mean camber line, right? And if I have an equation that talks about the distribution of thickness at each and every x, if I have the corresponding thickness distribution about y, about mean camber line, okay? And if I know the slope at each and every point of this mean camber line, I will be able to plot this aerofoil, right? What do I require here? Let us say this is my chord, no? Chord of this aerofoil as well, okay? Now for different locations of chord, what I require is, what will be my y of camber line at that corresponding x, right? Y of thickness at that corresponding x, and theta of the camber line at that x. If I have this information, then I will be able to figure out what is the corresponding upper and lower surface, right? Coordinates of upper and lower surface. So let us see how. Right? Now let us consider a point on the x-axis, let us consider a point on the chord, right? And the corresponding, let x on the chord, right? Now what will be the corresponding point on the camber line? From this you will get to know what is the corresponding point on the camber line, right? So this is my corresponding coordinate of the camber line. Now I know the slope here because theta of the camber line at that particular x I know, right? If I draw a tangent, right, theta of c is equals to d by c by dx, right? if I draw a tangent at this point, right? So now thickness is perpendicular, right? Thickness is measured perpendicular to this mean camber line. So if I have to draw the thickness, I need to know what are what is my, if I have to draw perpendicular, I need to know what is the reference here, right? The reference here is the tangent, right? So perpendicular to this tangent, I have this y of t. See, although this need to be more closer so that it looks symmetric, right? So consider this is a symmetric, understand? Symmetric thickness distribution, although it doesn't look like, but please consider this, right? Now you have this as y of t, and the same y of t you have it here. Now what are these coordinates then? Right. So if I draw a local horizontal here, which is parallel to this, right? Say this is my white line which is parallel to this. So this is parallel. Right? So this perpendicular component, so this two will be perpendicular and the corresponding angle will be theta here. Right? This angle will be equal to this angle, whatever I have. Right? And y of t, if I have a cos component of it, right, you will get this height, and you know this height, right? So this is, let us say this point is y of c comma x of c. Right? This height is, this particular height I have here is y of c, this is x of c. So I get this y of c from here. For a particular x, I know what is my y of the mean camber line, right? Now the point A, say, and there is a point B where I have xa, ya and xb, yb, right? So xa is equals to, I know this total distance. If I know this distance, say this is my xa, this is my xa, right? If I know this distance, if I subtract this, otherwise to get this xa, if I know this distance and if I subtract this distance, right, I know what is xc. If I subtract this horizontal distance, right, I will get to know what is my xa. So xa is equals to xc minus yt sin theta of c at that particular x, yt at that particular x, right? What is y at point A? Is yt, yc, this yc, this is horizontal, right? So parallel to this line. This distance plus this distance, this is again perpendicular to this line, right? So this total distance will be, this is ya, right, which is a summation of yc plus this particular distance. So yc plus yt of cos theta of c at that particular x. Right? Similarly, what is xb? So this distance plus this distance, right? xa plus yt of x into sine theta of c at that x, and similarly yb. yc minus yt into cos of theta of c at that particular x. Okay, got it, right? Now if you look at this, see yc is how much? Yc is this much, yt is this much, like yt cos component is this much. Here yt is this much and yb is this much, no. What? So okay, from here, right? I need to get to know what is the coordinate from here, because I am calculating this entire length. I know this length. If I want to know this length with respect to this chord, then I have to subtract here, right? So what happens is this becomes a negative quantity. That's why you have negative axis, negative y-axis here. Here it's a negative y-axis. Okay. So assuming the chord line is your x-axis, then you will get the negative y coordinate there, right? So you have xa ya and xb yb. So for at each and every point you can. So if you can find out the corresponding upper and lower surface coordinates for a given chord, right? Or for a given point on the chord. Yeah. Are we done? What about leading edge radius? So consider this is my leading edge. You know the slope at that particular point. Draw a tangent, right? Draw a tangent to this mean camber line at that particular point with the slope equal to the slope at that particular chord location, right? Now measure the radius along this chord line and draw a circle by using that point as a center. Although it is not exactly the same, draw a circle, so that should become tangent to the upper and lower surface, right? So this becomes the leading edge radius. Okay. So to define the aerofoil, what we need is camber equation of mean camber line or camber line, and equation for thickness distribution as a function of chord, right? And theta, or the slope of this camber line, as a function of chord, and the leading edge radius, say zeta, rho prime, right? Rho prime is your leading edge radius. Okay.